because there's a lot of subsystems, and they each do a different task inside the detector. But they all have, there are different categories. So one is trigger detectors. So we have about 100 collisions per second, so we have to figure out when we had a collision. And we have to do this automatically because it's not like you can say, oh, there's a collision, now start taking data. We have to have detectors that look and tell us, now automatically start taking data. Then there's tracking detectors. So we have all these particles created in the collision, and we try to look to see where they went. So there's a subset of detectors that look and tell us where the particle went. What kind of particle was it? There's all these hadrons. We try to figure out what it was. And we have special detectors that are optimized to do that. And then we have calorimeters that tell us how much energy does the particle have. And then just a little bit over a year ago, we had the first proton-proton collisions. It was a really big event and a lot of fun. I was there. This is a picture of me in the control room. And there I'm actually pointing up at the screen and saying, everybody was running around taking pictures. If you point at a screen and look like you're explaining something to someone, it'll make a better picture. Oh my God. Someone snapped a picture of that. And there was also a picture of someone was taking YouTube videos. So my parents-in-law saw me on TV. And they're like, oh, we saw you on TV. That was fun. And there was a lot of champagne. Here you can see a picture of all of the champagne bottles that were open. So this is where a European lab is different from an American lab. Oak Ridge actually has a no alcohol policy, so if I even have a bottle of wine in my trunk, I can get kicked out of the lab, even if I don't drink it. Here you can see an example of an event display from a proton-proton collision. So these are where you see all the tracks coming out. And this is looking, the cylinder is wrapped around the beam. And then the hits are where you see little calorimeter hits. So this is where we've measured the energy of the particle. Proton-proton collisions don't have that many tracks. And so at least people in my field, we think, oh, this is easy. There's only about 30 tracks in there. This is what a lead-lead collision looks like. And we have to take all of the information in there and try to sort out what particles were created and what types of things we have going on in this collision. So now I'm going to steal a movie from Atlas where you can see ions going around the collider, and what happens is they come together and collide and create particles. So now here you can see you're going along, that's the lead ion, and it's coming in with another, it's approaching another lead ion in the center of the Atlas detector. Particles are created, tracks come out, and then here you see all of the hits in the calorimeters. So I believe this is actually I think this is a simulation of an event in Atlas, but this is roughly what they look like. They made a really cool display, so let's do it. And then this kind of shows you a breakdown of the experiment. Roughly 1,000 people. This sliver right here is the people who come from the US. So we're kind of a minority. And that's fun. I have friends all over the country, all over the world, and I go visit them when I go to conferences. I'll spend a couple extra days in Lausanne. And then I'm going to talk about one result before I talk about how I got to where I am. But these are, one of the first questions is, how do we know that we formed this really exotic matter? I'm going to focus on this first one because it's been causing a lot of excitement lately. That basically, if we have high energy quarks, we can see that they get absorbed by the medium. And we also have other indications that we see that it actually looks like, it behaves like a liquid made up of quarks and gluons. And what we get out is roughly at equilibrium. So we see, so you can have chemical equilibrium, you can also have equilibrium between the types of hadrons that you form. And it's hot enough that we think that we formed it. And each of these could be its own very long talk, so I'm going to focus on this one right here, because this is very closely related to what I do. So we've created this thing, we want to measure its properties. It's hard because we can't create a big pot of it and poke at it and see what it does. So what we do is kind of analogous to spectroscopy. So you guys in some intro chemistry lab have done spectroscopy where you shine light through a sample and you see how much light is absorbed and you can determine the properties of whatever's in solution from that. We want to do something similar, but we have 100 of these collisions per second. We can't get the light in there at the right time. So we use things that are created in the collision. So one of those things, you can get a quark in one nucleus and a quark in the other nucleus coming in, hitting each other. They scatter off of each other like billiard balls. And then we look for evidence of one of the quarks, and we look for the other one that should have gone through the medium. And of course you can't see three quarks, so what you actually see is a little spray of hadrons in one direction. And here you can see, this is again from Atlas, this is azimuth, so if you wrap this around, this is what you would see on the outside of the detector. And so you see sharp peaks from each of these outgoing quarks. And then when you look in some of the heavy ion collisions, you see one peak, but you don't see the other. You kind of see some bumps in the right place. But what we think is happening is that it's not that, obviously the energy from the quark doesn't go away. Energy is still conserved, but the quark has had enough interactions that its energy goes into the medium. It gets absorbed by the quark gluon plasma rather than coming out. And this came out in November of last year, so this is a really exciting hot field. And so far we've learned, okay, we've got a very hot, dense liquid of quarks and gluons. This is the lowest viscosity fluid that we have ever measured. We don't know of anything that exists with less viscosity, and it might even be, it might even reach some lower limits of how low viscosity can go. And it's the most opaque thing we've ever observed. We can't, nothing comes out of it. And there's, now that we have the LHC, we're able to actually start measuring some of the properties of this in more quantitative detail rather than just saying, gee, it's opaque. So, it's exciting. And then this is a bit about me and how I got where I am. I apologize for the small font. I kept thinking of additional things that I wanted to slip in there. I'm a postdoc. I'm on 2 experiments. I got my undergraduate degree at Colorado State University. I was a bit indecisive, so physics, biochemistry, and physical science, and a little bit of chemistry and math and German. I actually started as a biochemistry major, and I had not taken physics until the 2nd year of undergrad, and I decided at the 2nd semester, my 2nd year, I went into the man who became my advisor and I said, well, I'm a biochemistry major, but I'd like to add a physics major, and I want to spend a semester abroad, and I want to graduate in 5 years. on the plan. He didn't laugh me out of his office, and he wrote